Alright, this lecture is going to be on lift. Now, we have covered the important parameters that we've seen: density, viscosity, velocity, how they affect our flow regime between laminar and turbulent, and you've had some practice working with some of the calculations, basic calculations, to come up with the Reynolds number that's going to be important for the regime. But now let's go through and actually use it for some important calculations, the lift on an airplane. So in your notes there's a better picture of an airplane, but let's just, for formality's sake, talk about lift. So lecture 1.6. So, if we have a plane, I'm just going to represent it as a line. But this is going to be our plane that we are having. So if we had a very, very thin plane, very, very thin, and looking at it in the profile into where we have the board, we would define drag. Drag is going to be a force. We define the force of drag that's going to be along the flow or along the profile of the aircraft or wing or whatever object you have. Then we'll have, going up, is the force of lift. That's going to be what we're focusing on today. Also, what we have is we have pulling down the force of gravity. The force of gravity holds us to the earth. And then if this is a plane that's going to have propellers or a turbine engine, you're going to have the force of thrust. That'll be your force of thrust that you'll have. So what happens is the plane moves forward. The motion moving forward, we're going to have force of drag slowing it down. But the important part with the plane is the force of lift. What we're going to go through today is quantifying some important parameters to allow us to calculate the force of lift. So, force of lift is up. Force of drag is going to be resisting the motion. So, if we have a flat plate, now this is not going to be specifically a plane. There are some theoretical calculations to come up with the important quantities, and we're going to go over those today for a flat plate. So let's go over those right now. So if this is going to be our flat plate, we have a flat plate that is going to be in a flow of air, a flow of water. Well, when we're dealing with airplanes, it's going to be a flow of air. The air is going towards the plane, or the plane could be moving relative to the air. So the plane can be moving, or the wind can be moving. So when we get into performing experiments, the wind tunnel, the plate stays still, and we have the air flowing over it. It's going to allow us to make some useful calculations, but that will be in future lectures. Right now, when a real plane actually moves relative to the air. So we know from our previous lectures, air has a velocity, has a density, and a viscosity. So for what we're going to be doing in class in our experimentation, actually air is going to be moving relative to the flat plate. But the flat plate could move relative to the air. The important parameter on our flat plate is going to be its area. And then also the angle at which it is tilted at relative to the flow. And we're going to call that alpha. Alpha is going to be the angle of the flat plate. So we can have a flat plate completely flat in the flow, or we can angle it up so it increases the lift. Alright, so now that we understand we have velocity, density, viscosity, the area of the plate, and the angle that it's going to be held at. So, what is known, this will also, more of these details will be presented in future lectures. But right now, let's use some of the results of our dimensionless numbers. So we know our force is going to be a function of each one of these parameters. But we can simplify some things, so we can say our force of lift is just going to be a function, call it f, of Reynolds number and angle for our flat plate. Force of lift, actually let's just call it a function. Different function, let's not call it f, but let's call it g. So it's some sort of function. When I mean function, it's going to be some sort of algebraic formula of Reynolds number and alpha. So as your Reynolds number changes and your alpha changes, the force of lift is going to change. What I'm going to do is I'm going to give you what that formula is going to be. So we're going to have the force of lift equals the coefficient of lift. That's going to be an important parameter. I'm going to give you a theoretical calculation for a flat plate, but when you perform experiments, all of this information is buried in there because the area and the profile, shape, when I say profile, of your wing can change. So, coefficient of lift multiplied by 1/2 multiplied by rho v squared a. So find the force of lift. It's the coefficient of lift multiplied by 1/2 multiplied by rho velocity squared times by the area. FL is our force of lift. It's going to be a lift force. That's going to be pushing the plane up. We're not going to worry about drag or thrust or gravity right now. But that's going to be the force of lift that is going to be pushing up on that plane or flat plate. Force of lift up. Force of lift is FL. This is the coefficient. Coefficient of lift is calculated by experimentation. However, there are some, and we're going to go over that, what you can use for a flat plate. V is velocity. A is area. We'll put back over here rho is density. And mu is our viscosity. So, we know the coefficient, we know the density, we know the velocity, and we know the area. We can calculate what the force of lift is going to be. And we're going to do some of those in a little bit. Flat plate. A flat plate works somewhat nicely for a lift. We're going to have that for our experiments in class. However, there's better shapes to increase the coefficient of lift. If the coefficient of lift increases, gets bigger, we'll see the force of lift will also increase. So therefore, it'll be easier for our plane to fly. So, some of the important airfoils that can be made. Airfoil would be the representation or the shape that you would have for a wing. So here's our wing. You notice that a wing is never or not typically a flat plate, but again it's an approximation. And if we have our free stream coming in, what will happen is your free stream, depending on the velocity, will take a different profile around it. So this may be coming in and you'll have a point of stagnation. And then you'll have these streams, we'll call these streamlines, going around it. This is going to be a stagnation point. Stagnation point is going to be where you have zero velocity. Zero velocity here. Here streamlines are going to deform around your shape. The flow will go around, then you can have flow coming off, and your flow representing and deforming around your shape. let's represent our airfoil. Better, and we'll represent that in blue. There's going to be your flow going around your airfoil. What you've got now is you'll have going up is the important force of lift. Force of lift raises this up. As long as this keeps moving or the air keeps blowing, your wing will rise due to the force of lift. Alright, well that's nice. However, how do we get the coefficient of lift? Again, this is where the course will be going, and we'll build on this, but it's experiments. You measure the force, you measure these other parameters, and then for a particular wing, you can get its coefficient of lift as a function of Reynolds number and angle. But for a flat plate, there's a way to approximate. The coefficient of lift for a flat plate is going to be given by 2 pi sine of alpha. Alpha is our angle that our flat plate will be lifted at, and it's going to be measured in degrees. Or it can be approximated as 0.11 times by alpha, where again alpha is going to be measured in degrees. And we call alpha our angle of attack. The angle that the flat plate will be entering the free stream. And it's measured in degrees. Alright, so now we have a way to calculate the coefficient of lift as long as our flat plate has an angle of attack, alpha. Alright, let's go through some example problems. So we're going to calculate lift and the coefficient of lift for a few different configurations. So the first thing is that we're going to have is we'll have a flat plate. And the flat plate will have the dimensions of 2 meters by 1 meter. So imagine that this is going to be 2 meters by 1 meter, and it will have an angle of attack as long as we have the profile of air going along it. The air will deform and you'll have a force of lift resulting. So 2 by 1 flat plate, and again we remember what a 2 by 1 meter is, remembering from our board. So let's do this first. Let's have an angle of attack of 4 degrees. So it has an angle of attack of about 4 degrees. It's either moving relative to the air, 22 meters per second, or air is blowing over it with a free stream velocity of 22 meters per second. And the density of the air is going to be 1.201 kilograms per meter cubed. So the air has a velocity of 22 meters per second, a density of 1.21, and what we see from this one, from our calculations of force of lift, the coefficient of lift doesn't need the viscosity. But if we want to get the coefficient of lift, which we'll go into a little bit later in this lecture, but we have a way to calculate the coefficient of lift which does not need viscosity. Alright, so let's go through and let's do this calculation. Alright, the coefficient of lift, using our formula, 0.11 times by alpha. 0.11 times by alpha, and alpha is going to be 4, gives us a coefficient of lift, 0.44. It's pretty straightforward and easy. Now we can calculate the force of lift. The force of lift is going to be 1/2 the coefficient of lift, rho v squared a. 0.44 divided by 2. 0.44 is our coefficient of lift. The 1/2 out in front. The density is 1.201. The velocity is 22 squared. And then we also need to multiply it by the area. 2 by 1 gives me an area of 2. This results in a force of lift of 260 newtons. 260 newtons of force. I'll just pause a second and let everybody perform this calculation before we move on to another calculation. Alright, let's keep the same size flat plate, but now let's do an angle of attack of 1 degree. 1 degree angle of attack, and again, the velocity either of the flat plate is going to be 12 meters per second, or the air is blowing over it with a velocity of 12 meters per second. And the density in this case, say we have a little bit less dense either fluid or a little bit higher up in the atmosphere, the density of the fluid that's moving over it, in this case it's gas, is going to be 1.001 kilograms per meter cubed. Alright, now let's see what the effect of a smaller angle, smaller velocity, and a decreased density has on our force of lift. So the first thing is we need to come up with the coefficient of lift. Coefficient of lift is 0.11 times by alpha. Alpha is 1, and we get 0.11 times 1 is the magical 0.11. Force of lift, 1/2 the coefficient of lift, rho v squared a. 0.11 over 2, the density in this case is 1.001, the velocity is 12, and we have to square that. And the area, again, the area of the profile, the area that's going to be having the force pushed on it, making a stress, but we're looking at the force over this whole area, A, which is going to be 2. Put all the numbers in your calculator, 0.11 divided by 2, multiplied by 1.001, multiplied by 12 squared, multiplied by 2, and you can come up with a number. This is roughly 0.5, that's 144, that's roughly 1. And when you put this in your calculator, you should get 16 newtons. Much different magnitude of force, greater than 1 order of magnitude. 1 order of magnitude is basically multiplying by or dividing by 10. So 160, well this is 16, but 1 order of magnitude would be 160 or 1.6. So 1 order of magnitude and then doubled. So things affect the force of lift, which is important. It's going to affect how well the plane will be able to fly or maintain altitude, because we have to overcome the force of gravity, which is always pulling it down. Let's do one more example. So this is a way we can calculate the force of lift of a flat plate. But let's go through now and let's determine what the coefficient of lift is. And this is what you're going to be doing and performing in later experiments in class. Alright, so let's determine we're going to determine the coefficient of lift for the following conditions. Let's say we've got the area of profile equal to 5 meters squared. The velocity is going to be 10 meters per second. The density is going to be 1.200 kilograms per meter cubed. And let's say the measurement force of lift of the model in an air chamber is going to be measured to be 100 newtons. So you have your airplane in a flow chamber. And then you're able to measure the force of lift of the air blowing over it. That way, you measure the actual force of lift. In this case, it's 100 newtons. You know the velocity, the density. Right now the viscosity is not going to be used, but that would be important to determine the Reynolds number, and we'll go into that a little bit more in later lectures. But we can come up with the coefficient of lift for that real wing, or real model of a wing, which is very, very important because coefficients of lift are quantified for many different wings that are developed and designed. So, using this formula, force of lift equals 1/2 coefficient of lift rho v squared a. You can solve this algebraically for coefficient of lift. So it's 2 times the force of lift divided by the quantity of the density, the velocity squared, and the area. We can easily put this into our calculators. And we come up with a quantified value of the coefficient of lift as 0.33. Take a measurement of the force, take a measurement of the density, you design your area of your wing, and you can have force of fluid around it and measure the velocity, comes up with the coefficient of lift. Then you're able to actually scale that up, and again that'll be in later lectures of how to use these values from model to prototype, which is very, very important. But we'll hold off on going through that any more discussion. But I want to discuss what the coefficient of lift is in a little bit more detail. And again, to be careful with the coefficient of lift, this is going to be an approximation for a flat plate. Coefficient of lift is a dimensionless number. And again, remember that the coefficient of lift includes many assumptions about our flow. And again, these assumptions are going to be beyond the scope of this particular class. To do this fully correctly, to perform this, you have to take into account the conservation of mass, momentum, and energy to somewhat simultaneously. And again, those are going to be somewhat complicated formulas that are going to be nonlinear in nature. And to perform this, if you want to study this further in a more in-depth class, which leads you to CFD, which stands for Computational Fluid Dynamics. So you can take a class on computational fluid dynamics where you can use computer models to perform this. There's not very many closed form solutions. This is again an approximation which takes a lot of this into account to come up with a way to approximate the coefficient of lift for a very nice regular geometry. And again, in the notes, Wikipedia, you can see how on a real plane the wingtip creates vortices. Alright, that concludes the lecture for coefficient and force of lift.